All right. So today we are going to go ahead and finish up our talk of different types of functions. This is going to be the last lecture before your quiz, which when you are viewing this will be tomorrow. That'll be Friday this week, the 2nd, I believe. But your quiz is going to be on sections 1.1, 1.3, and 1.4 in your book. You don't have to worry about sections 1.2, and you will get notes. So I would strongly recommend taking them during this lecture. Let's go ahead and get into it. We are continuing our types of functions discussion with nonlinear functions, increasing and decreasing functions, average rate of change, and the difference quotient. So to start, nonlinear functions. Functions that are not linear are referred to generally as nonlinear functions. That is pretty redundant. Hopefully that makes plenty of sense to you. But if it's not a linear function, it's a non-linear function, or it's not a function. It can be one of the two. The following are true of nonlinear functions. So the graph is not a straight line. Again, that's pretty obvious. You can get that from the name. They do not have a constant rate of change. So that means that there's not going to be a constant slope. The rate of change is going to be constantly changing as the graph goes along. They cannot be written as f of x equals mx plus b. They're always going to have some slightly more complicated formula than that. And they can have any number of zeros. And so in this case, we're talking about zeros. If you think of zeros as a point where it crosses an axis, right? The y-intercept is a 0 on the y. We're talking about, in this case, zeros on the x. So it can hit multiple times on this, like this. But it should still only hit the y-axis once at most. There are many different types of nonlinear functions. You're probably familiar with a couple. Let's look at a few examples that hopefully you've all seen before. I would think you have. This is f of x equals x squared. This is f of x equals the square root of x. This is f of x equals x cubed. And this is f of x equals the absolute value of x. And so all of those you could graph pretty easily on your own in your calculator or on paper if you really wanted to, but these are all nonlinear functions. You'll notice that this one, the absolute value of x, where's my pen? This one over here, it is kind of a line going down and kind of a line going up, but because it's not a straight line all the way through, it's considered nonlinear. So nonlinear functions and linear functions actually can be said to be increasing or decreasing based on the slope at any given instant. So if you think of real life examples like the stock market, the price of gas, the balance in a bank account, the numbers go both up and down over time. Or if it's a bank account like mine, it looks like it's mostly down, but that's neither here nor there. A function is considered increasing if the output, f of x or y, is increasing as the input increases. So what that means is, oh, sorry, I've got some cords in my way. What that means is if you move left to right across the x-axis, if y is going up, that is increasing. So that line would look something like this. A function is considered decreasing if the output is decreasing as x increases. So that means as you go left to right this way, y is going down. So something like this is decreasing. One way you can think of it is if you draw a person trying to walk up it, or trying to walk on the path of the graph. If the person is walking downhill, it is decreasing. If the person is walking uphill, it is increasing. So the following functions that we're going to look at have intervals in which they are increasing and intervals in which they are decreasing. So this was the y equals x squared, and this is the absolute value of x. We can write these intervals using interval notation. So if we look first, they both actually have the same intervals. They're both decreasing on this side of the y-axis, and then they're both increasing. Let me change the color. Oh, try that again. They are both decreasing on this side of the y-axis. And then let's see if we do this. Let's use green. And then they're both increasing on this side of the y-axis. And that's the same over on the other side as well. So we can write these intervals using interval notation. In both cases, the function is decreasing when x is less than 0, and it's increasing when x is greater than 0. For both of these functions, the slope at 0 is actually 0. This one, I think it's undefined. But there's not an increasing or a decreasing slope at 0, so 0 is not included in either side of this function. In interval notation, the functions are decreasing from negative infinity to 0 and increasing from 0 to infinity. And because that 0 is neither increasing nor decreasing, it's not included on either of these. And then the infinities, obviously, we always end with a normal parentheses. So this is the same notation you would use to write domain and range, but in this case, we're looking at whether the function is decreasing, which again, if we draw our little person in here, we can see that it is decreasing. If we draw our little person over here, you can see that this one is increasing. As they walk to the right, they're always walking to the right. That was a bad arrow. So yeah, that's just another way of writing those intervals instead. So a little practice for you. Is the following increasing, decreasing, or both? So first, let's look at the graph of y equals the square root of x. Now, some people get tricked by this because this slope starts really steep and then it starts to kind of curve down a little bit. But if you draw a person on here and you kind of imagine them walking this way, they're never actually walking downhill. They're always walking uphill. So this one is always increasing. This one has a similar thing going on. This is the y equals x cubed, or f of x equals x cubed. So this one is very steep right here, and it kind of evens out, and then it gets steep again. But at no point in time is this function actually decreasing, so it's going to be increasing the entire time. And then this one, this is e to the negative x. This one is decreasing the entire time, even though it's starting to kind of curve up towards the end. So this one is going to be decreasing. So we've got increasing, increasing, and decreasing. Okay, so let's look at a real life example. In this case, this is actually the same example that your book uses, but we're going to look at a graph of the gallons of water in a small swimming pool over time. So that graph looks like this. You've got gallons on the left, time in hours on the bottom. You'll notice that it's increasing from 0 to 4. So in this section right here, it is increasing. Then for a while, from 4 to 8, it stays the same. So it's neither increasing nor decreasing. Let's maybe do that in blue, I think. Yeah, let's go like that. And then on the other side, it is going to be decreasing. So that's from here to here. So from 8 to 12. And these are all x points, just in case you're, this is x, this is x, x1, x2, x2, x3, x4, x3, and x4. So one of the things that is useful to do when you're looking at graphs like that, or graphs in general that have that are nonlinear, is the average rate of change. And so in order to do average rate of change, you have to be between any 2 points on a graph. So you have to pick 2. You could theoretically do it between 3, but there's not really any reason to. Generally speaking, what that average rate of change tells you is it's an average. So like if you were driving your car 10 miles and you got there in 30 minutes, your average was 20 miles an hour, even though probably part of that time you were, going slow, might have been stopped at a light, you might have been going faster at some sections. You can calculate the average rate of change by using those 2 endpoints. So this is similar to calculating the slope of a linear function, which you'll remember is the y2 minus y1. So this is the change in vertical height, or the rise of your change over time. And then this is the horizontal distance, or your run. So it's rise over run. You've probably heard that before at some point. But you basically do the same thing. So if we go back to our gallons of water in a pool, we can calculate the average rate of change between multiple different points, and it's going to be different. So let's start with, if we do between the points last time that we used as x1 and x2. So that's 0, 0, 0. Oh, sorry. I can't write that low apparently. So 0, 0, and 2, 4, 500. So if we plug that into our formula, our y2 is 500 minus our y1, which is 0, divided by 4 for our x2 minus 0 again. That equals 500 over 4, or 125 gallons per hour in this case. So that's our average rate of change from those 2 points. But if we go now from the origin, 0, 0, right here, that's also, by the way, equal to the slope of this line, because this is a linear function from here to here. So if you calculate the slope of this, it's going to be the same. But this time we're doing this line right here. So the average rate of change, whoops, that's a terrible line. Average rate of change from there to there. So this time we're using the points. Here, let me erase this. It'll be easier to see. So from there to there. And this time we're using the points 0, 0, and 8, 500. So in this case, we're going to do the same thing. Our y1 or our y2 is 500 minus our y1, which is 0. And then that is over 8, which is our x2, minus our x1, which is 0. That equals 500 over 8, or what is that, about 50? I don't have a calculator. Can't do it off the top of my head. It's should be 56.5, I think. 57.5. 57.5. There we go. Okay, so it's 57.5 gallons per hour. Okay, and then the last one, we're going to look at what happens if we do it from 0, 0 to 12, 0. So this time we're going from here to here, and looking at that, you can probably already guess what the rate, or the average rate of change is. But the other point is 12, 0. But if we do our y1 minus our y2 minus our y1, we get 0 minus 0 over 12 minus 0 equals 0. So the average rate of change between here and here was net 0, right? This, if you picture this small pool starting with 0 gallons of water, it ends with 0 gallons of water. So effectively, its net change was 0. But during the middle, you had different points in time where it had more water than that in it. And so at that point, it had rates of change. You could also calculate a rate of change from like here to here or here to here, and those would be negative. So you could calculate, I mean, you could calculate a rate of change if you wanted from like here to, here or something. I don't know why you would, but you could do that if you wanted to. The point is just that you can calculate the rate of change between any 2 points, and it's going to be different depending on where those points are in a nonlinear graph. Okay, this is going to close for a second, sorry. Open that back up. I messed that up, hit the wrong button. Try this again. Okay, so we're past this. Okay, so the last thing we're going to talk about, and you're actually going to have a second video on this, it's going to go into a lot more detail. This is probably the most difficult thing in this first section of units, and this is the difference quotient. So it is helpful in general in math, but especially in this case, to find general formulas for things. So in this case, we're looking for a general formula for the rate of change over any given points in a function. This general formula we call the difference quotient. And what that looks like is this. So it says f of x plus h minus f of x divided by h. That equals the average rate of change equals average rate of change across the points f of x to f of x plus h. And the other video is going to go into much more detail on this. It works through a bunch of examples and stuff, so hopefully that'll be a lot more clear than this right here. We're going to talk about this more probably in class too. So h represents the difference between the initial point x and the final point h. So all this is saying is like, let's say you wanted, your initial point was like, let's say 212. The y value doesn't really matter here. H would just be whatever you have or whatever you change x to, right? So like, let's say we change x to 6 and maybe our point is 23 or something. H would be 4 because h is going to be the difference between x and or x2 and x1 in this case. So 6 and 2. H is just the distance you've traveled left to right on the graph in between any 2 points, and that'll change when you make the general formula. This is going to make a lot more sense when you watch the second video, so go ahead and do that now, and then we will talk about this more in class today, so that hopefully we can clarify it for you guys. But that is it for the rest of this unit, and once you've finished that second video, hopefully you're ready to take on your last assignment before our quiz tomorrow. So I will see you guys in a little bit.